Okay, and so let us go to integration of rational function. So it can be a long and boring chapter. I will try to be quite fast. So integration of rational function. I have to say that here I will follow with giving not so many details. The book in which, in my opinion, this method is explained at best, which is the book by Fabio Nicola. Okay, which is in Italian, but of course, very basic Italian, and basically it is mathematics. So first step is the following. So if I receive this method, so first step. First step is the integration of some prototypes. And it is very easy and well known what are these prototypes. Which are 1 over x to the n, then x divided by 1 plus x squared to the nth power, and then 1 divided by 1 plus x squared to the nth power. Okay? The first two integrals are extremely easy. So, and this you already know, it is in the table of integral, so it is equal to log of the absolute value. Always remember the absolute value of x plus c if n is equal to 1. And it is minus 1 over n minus 1 divided by x to the power m minus 1 plus c if n is larger than 1. Minus 1 because this is x to the minus n. When you integrate here, you have minus n plus 1. Okay? And this is the first integral that you have to know. The second integral, the second prototype, is the following. X divided by 1 plus x squared to the n. This is easy. We just saw one of those because we just had to multiply by 2 here in order to obtain, I write it everything, in order to obtain here the derivative. This is 2x, sorry, 2 and 1 over 2. So 2x divided by 1 plus x squared to the n. So, and this is, so 1/2, and here in the integral you have 1 plus x squared prime, and here 1 plus x squared to the n. So here you can just change variable and pass to the variable 1 plus 2x squared, but this is this is not really necessary. So, or you just write 1, so you use the variable y is equal to 1 plus x squared. So dy is 1 plus x squared prime dx. This is the trick of change of variable. So here you have 1/2, sorry, 1/2 dy divided by y to the n, and so we are led to the previous case. So we have 1/2 log absolute value of y plus c if n is equal to 1. Otherwise, we have minus 1 divided by 2 n minus 1, y to the power n minus 1 plus c for n larger than 1. So we use the same formula here, sorry, the same formula here, but for the variable y. Very easy. Okay, and now we substitute y with 1 plus x squared And so we have 1/2 log absolute value of y. Y is x squared plus 1. So since 1 plus x squared is always larger than 0, this is log without absolute value, just the brackets, the ordinary bracket is enough for n equal to 1. And this is 1 minus 1 divided by 2, n minus 1, times 1 plus x squared to the power n minus 1 for n larger than 1. Okay? And so, so this is for what concerns this 1, 2, 3. So we here have 1, 2. Let us go to 3. 3 is the more complicated of these prototypes. The first thing that you have to notice here is that if n is equal to 1, we already know. We already know this guy. So if we have 1 divided by 1 plus x squared to the n is equal. So if n is equal to 1, this is easy, and this is the arctangent of x plus c. If n is equal to 2, it is already much more complicated. If n is equal to 2, you can use the following trick. So 1 divided by 1 plus x squared to the square. You just complete here to obtain the binomial at denominator. So how to do that? You write here 1 plus x squared minus x squared divided by 1 plus x squared to the square. So here you have 1 plus x squared divided by 1 plus x squared to the squared dx. And at the end, minus x squared divided by 1 plus x squared to the square dx. And so here you have, again, dx divided by 1 plus x squared. And this is the first that we already know. And the second, here, there is a smart trick, which is the following. This is x times x divided by 1 plus x squared to the square in dx. And here, you go by integration by part, because this is easy to differentiate. And the other term is easy to integrate, because here you write here 2. So you are in the previous case at the end, you write it here 2. So here 1/2. And so let us go forward. The first integral is the arctangent of x, then minus 1/2. And so you you don't touch this guy here. This is x. You want to differentiate. This. And then you want to integrate the other. And the other is simply minus 1 over 1 plus x squared. Because when you differentiate it, you get plus 1 over 1 plus x squared to the square times 2x. So this is correct. Then here you have minus, minus, plus. Then here, when you integrate by part, you have to have the other sign. So minus 1/2. This time you differentiate x, so you don't have anything here, and you remain with dx divided 1 plus x squared. And so it is solved. There is this sort of magic here, and you have equal to. So here you have arctangent minus 1/2 arctangent, so 1/2 arctangent of x, and plus 1/2 x divided by 1 plus x squared in dx. Okay, perhaps here, let me verify this guy here, and if we differentiate it, we have 1/2 arctangent of x plus 1/2 x divided by 1 plus x squared. So you have 1/2 1 plus x squared plus 1/2 1 plus x squared, and here minus minus x 1/2 again, 2x divided by 1 plus x squared to the squared times x. Okay, so here you have 1 divided 1 plus x squared minus x squared divided 1 plus x squared to the squared, and we write it again as 1 plus x squared to the square, and here 1 plus x squared minus x squared, and this is correct. Okay, this is just to verify. So this case is already a bit more complicated. It requires to be smart already when n is equal to 2. When n is larger than 2, so for every n different from 1, so also n larger than 2, you have to use the same formula as before, just generalize the method used for n equal to 2. So you write that 1 divided by 1 plus x squared to the n is equal to 1 divided by 1 plus x squared to the power n minus 1 minus x squared divided by 1 plus x squared to the n. So notice here you have a reduction of difficulty, because you can imagine to compute, we already computed n equal to 1, n equal to 2. Here, if we compute the integral for n equal to 3, we already have here the integral for n equal to 2, and then here it can be made by integrating by part. Okay? So, just integrating we have that the integral of dx divided by 1 plus x squared to the n is equal to the integral with 1 degree less a denominator minus x squared divided by 1 plus x squared to the n, and so integrating by part, integrating by part the last one, we have that dx divided by 1 plus x squared to the n is equal to the integral dx 1 plus x squared to the power n minus 1 plus x, as before. Here we have the x, and then we have to integrate the other part here, because again x squared is equal to x times x. So x divided by 2, n minus 1, 1 plus x squared to the power n minus 1, plus 1 over 2, n minus 1, integral of dx 1 plus x squared to the power n minus 1. Okay? And so then, you just sum these two, which are the same. Okay? Just sum in these two terms. Sum in these two terms, you have that the integral you looked for is equal to x divided by 2 n minus 1, 1 plus x squared n minus 1 plus, at the end the result is 2n minus 3 divided by 2n minus 2. Integral of 1 over 1 plus x squared to the power n minus 1. This is the very important formula, okay? Because this formula linked the integral you want to compute with the previous integral of the same type here. Okay? So the idea is to iterate the formula n times if you want to compute this integral here. But okay, this tells you that this integral is extremely complicated. We will never have to deal with such an integral, with an integral of such a complexity in our course and so on. So in this sense, you can be okay. I can reassure you on this. Don't worry. So you don't have to learn this formula by heart. But the point is that this formula can be very useful. And then perhaps I need another video to tell exactly what to do here. Okay.